Cm minus 1. Again, pick m to be 6 to easily understand it.
So that means
So C6, meaning now we already have 5 classifiers, we are adding the 6th. So the combined result from the 6th, that's what we call C6. C6 of x of I will be Cm minus C5 x of I. But C5 was already this whole expression over here. Right? So what do we have to do? Add alpha 6 times K6 of I. Correct? So, so basically, however many, so let's start from the beginning. In the beginning, what will be, let's say C1, right? So C0 of x of I, as you can see, what will we assume this to be? So C0 we'll assume to be 0. There's no classifier exists. In our indexing over here, 1 is the lowest index. Okay? So as you can see, then all we are doing is picking the very first classifier. Once we have picked the first, then second one will be based on the first one, and then whatever alpha 2 is, and so on. Okay? So to summarize, what I'm trying to say is the development over here goes like this. We already have m-1 classifiers and their coefficient somehow determined. How will we add one more classifier? And what will be the weight of that? So the classifier is m. So we want to know what will be essentially alpha m. So if we had 10 classifiers, right? Oops. Okay, hopefully, okay. So let's say we already have 10 classifier. Again, let's pick m equal to 6. So which means 5 have already been picked. We are trying to pick the 6th one.
Yep.
So how many are remaining if we had a total pool of 10 classifiers? 5 will be remaining, right? Because we have total K1, K2, let's say K10.
Okay.
5 up to K5, we've already assigned some coefficients, alpha 1, alpha 2, alpha 5. Okay, now we have to pick coefficient for the 6th one. Okay, and by the way, maybe this is the confusing part. When I say 5 have been picked, right, they don't have to be in order. So if we have 10 choices in the beginning, right?
Yep.
Which one will we pick? Whichever produces the lowest.
Lowest.
So it could be K7, it could be
exactly.
K8, right? After we have picked K7, as an example, how many are remaining in our pool? 9. So now we have to pick
4 more.
one of those 9 as an example, and so on, right? Okay, so anyway, to summarize, what I was trying to say is, suppose some classifier have already been selected and coefficients have been assigned. How do we add one more from the remaining pool? So this could be, let's say, classifier 3, classifier 8, classifier 9, classifier 6, classifier 4 are remaining. So this K of m could be any one of those.
Yep.
Okay, so we have 2 things to decide. Which one of these will be picked next, and what should be the coefficient of that. So that's the basic problem. If we can establish this recursive relationship, then like I said, we'll start from the 1, keep adding one more, keep adding one more, until we get to the end of the pool. As we add 1, we assign a coefficient. So Okay, so let's see what will be next. Okay. Now, some of you who are in the deep learning class, okay, if you recall, if we have, let's say, 10 class problem, like when we were doing the digit recognition, what was the activation function we were using?
Last was softmax.
Softmax, right? And remember what did if this is 0.3, what did the softmax try to do?
The maximum it was enhancing because you.
So it will do e raised power 0.3, correct?
Yeah.
And then sum of all the e raised power of these ones. So basically, it's trying to enhance, so whichever output is closer to our target, you can see will get enhanced more. So this is a standard technique in optimization theory and math. If we have a bunch of choices, we often use the exponential function to enhance the difference between the choices. Okay, so here too. Okay, the error function that we are creating over here, if you take a look over here, is basically the Cm minus 1 of x of I, if you take a look, is basically the decision of the sum of classifiers so far. If m is 6, as we go through, if m is 6, right? Meaning we've already selected 5 classifiers and we know their weight. So Cm minus 1, if you take a look, is basically a sum of all of these, the decision of all of these, right? Okay, so then we multiply it by yi. Can you guess what yi is? Expected output, which will be what? What are the choices for yi? 1 or negative 1. Okay, so let's go over here, how this will be done. Okay, suppose this one produces an answer, let's say 1.
Yep.
And the expected output is also 1 for this particular input. Then what will this term produce? E to the minus, expected is 1?
Times 1.
1 times 1, right?
Yep.
Okay, which will be bigger number or smaller number? As opposed to,
Small.
what if the classifiers, the sum of these produced a 1, but the expected was a negative 1?
Then it would be big.
Then it will be plus 1, right?
Yep.
So e to the minus 1 is when we have a correct match. And you can see there's a plus sign over here when it's incorrect. And once again, in the error function and the loss function, what's our goal? We want to produce lower number when it's correct or lower number when it's incorrect?
Lower number
When it's correct. So as you can see, for all over, n is the number of training data, right? For all the training data, it's checking is the output produced over here matching the expected output. And if it matches, as you can see, the exponent will always be a negative number. If it doesn't match, the whole exponent over here will be a positive number. Okay?
But we haven't been considering the right side yet.
The next classifier yet. Okay? But also, if you take a look over here, this yi has been added to the next one. See, there's a parentheses over here. There's
Yeah.
a parentheses.
So you were assuming if that entire thing is 1.
Yeah, so the overall cost is whatever existing classifiers are producing compared to the expected,
Yes.
plus whatever the new classifier is producing, whatever the weight is compared to the expected. So this will be our total loss function or total error function. Okay, it's pretty straightforward. I don't think it's that complicated, right? Okay.
So that I is basically like an index pointing to either a 1 or a 0 in a set of data, right?
Yeah, so I index is our iterating over the set of data.
Okay.
The M index is the classifier number.
Correct.
Okay, so if we understand this, rest is a tiny bit of manipulation tricks that the author does so that we can set it up, take the derivatives and figure out what should be alpha 1 and how should it proceed. So anyway, so let's go to the next equation. In the next equation, if you compare these two, okay, what you will notice is what we did is we split it in two parts. Okay, so this will become e to the minus yi cm minus 1 xi e to the alpha m km of xi, correct?
Yeah.
So if we now take this part and call this wi of m, so basically, so I is once again varying from what?
Number of
The inputs,
The number of data points, right?
Yeah,
Training data.
Sure.
So essentially, you can think of it, this is doing is, there's a weight associated with each data point, okay?
Yeah.
So whatever the current weight is with the data point gets multiplied by our new classifier to further decide which one of the classifiers and what should be the weight that will minimize this error, okay? So let me go a couple more steps, then hopefully this will start to make perfect sense. Okay, so anyway, like I said, all we did is we made this wi of m, okay? Then we further divide it into two subparts, okay? For those cases where it's correctly predicting, for those cases where it's not correctly predicting. So you can see yi equal to km of xi. So the expected is same as our new classifier. And if it is not the same, so we split it in two parts, right? Then, okay, further, this part over here, we called it WC, the correct sum of the correct weights. This is the sum of the error weights. Okay, what's our goal over here? Goal is to find the coefficient of the classifier that we are adding, right? In addition to which classifier? Okay. Anyway, if I did, for example, dE over d alpha, we'll be able to, and set it equal to 0, won't we be able to figure out the value of alpha? We already know WC is basically the sum of these, so let's go and see that derivative. Okay, we don't need to worry about this. So once again, let me write this on this side, E equal to WC
E to the base C, yeah.
e to the minus alpha m plus WE
C to the alpha.
e to the alpha m. So if I did dE with respect to d alpha m, what will happen to this term? This is E, by the way. What's the derivative of e to the negative alpha m?
e raised to x and
Comes
e raised to
down.
negative 8 times into derivative.
Minus A to the M.
Minus WC e to the negative alpha m, correct?
Into
Plus WE
e raised to alpha m
e to the alpha m.
into alpha m.
No. Alpha m is just a number, right? We're taking derivative with respect to one variable. E to the x, remember derivative is e to the x.
Yes.
So the second term stays as is, this gets multiplied by the negative.
Yeah.
Okay. All right, so this is what's being shown over here. Over here.
So minus
Do you see
comes down.
negative?
Yeah, minus
And
goes
then-
down, and then the same.
Correct?
Mm-hmm.
Okay, so now let's try to our goal is to set this equal to 0, correct?
Yep.
And then solve for alpha. Okay, so if we now set it equal to, let's see, from here, e to the, okay, let's multiply both sides by e to the alpha m. So if we multiply both sides by e to the alpha m,
That
Right.
drops off.
that drops off, becomes minus wc. This becomes
2.
2 alpha m equal to 0, right? Now move this
Over.
equal to we, or let me do it the other way. We e to the 2 alpha m equal to
WC.
wc. So then basically
ln.
this goes over we, right?
Uh-huh.
Then if I take the log of both sides,
Yep.
then this will become
Log of
2 alpha m equal to
log of
Log of
log of
W.
wc over we. And then alpha m becomes half,
Half.
1/2 of that.
correct?
What's the I?
Which I?
It's WC over WE. What's that?
Oh, that's my cursor.
Oh.
Okay, so now let's go one more step and then hopefully,
Yeah, log a minus log.
okay. So remember WC was basically the sum of the correct predictions. WE was the sum of the erroneous predictions, right? So WC plus WE is basically our total, okay? So as you can see over here, WC can be written as W minus WE, right? And divide by WE. Okay, so then further, if we define E of M, so E of M equal to WE over W. Okay, so we are defining it. Then this whole thing could be written as 1 minus EM over EM. Okay, and you can easily verify it. This will become 1 minus WE over W divided by EM WE over W, right? What does the top become?
W minus
W minus
W.
WE over W
and
divided by, which gets multiplied by
W upon W.
WE, right? WW cancels.
Yep.
So you will see this is exactly the same as the original. Okay. Okay, so now let's go to the algorithm. And so anyway, this is our main conclusion. Alpha will be determined by this particular equation, okay? And what is EM once again? EM is error divided by the W. Okay, so now let me show you the ADA Boost code. Okay, Okay, so suppose we have a pool of classifiers, right? Select the pool of classifiers which minimizes WE, correct? Once again, what is WE? You guys saw that
Yeah.
was
We select the number of correct,
where did it go? The number of incorrect
incorrect, yeah.
is oh yeah, WE was just the number of incorrects, right? It's the EM that I was looking for. So anyway, so we take, so this is basically sum of incorrect weights. Okay, so essentially think of this way: x1, x2, xn. So in the beginning, everybody has a weight. So it could be 1, or sometimes we make it a distribution. Sum of our distribution should always be 1. So if we have 100 samples, we'll make it 1 over 100, 1 over 100, 1 over 100, right? Okay, so let's pretend we apply the classifier 1, or I should call it K1. Of course, some of these it will predict correctly, some of these it will. So let's pretend somewhere over here x20 was correct, x35 was correct, x2 was correct, right? And everything else was wrong. So then what will be WE over here?
Solution obsessed.
WE is sum of incorrect weights, right? Incorrectly classified, those samples which were incorrectly classified, it's the sum of their weights. Okay?
97 over 100.
97 over 100. Because 3 we are assuming were correctly classified,
And then the rest.
97. So we are just so that's how we calculate WE, right? So hopefully this makes sense, right? Then after we have calculated WE, right? Then can we calculate EM? EM, if you recall, was what? WE over W. So if there's, usually, like I said, if we scale that, then the sum will be 1 anyway. So it's essentially, so what will be WE in our example if 3 were correctly classified and we have 100 samples?
97. Wait, no, the ones that are correct.
Yeah, I'm asking about EM. What will be the value of EM? If 3 were correctly specified, did we see this will be 3 over 100,
Yep.
right? And what's W?
100.
Each is, the weight of each is 1 over 100, right? So if we sum all the weights,
100.
it will be 1.
1.
So E of M will be 3 over 100. So anyway, so then what will be the alpha for that classifier? Meaning this
1 minus 3
1 minus 3 over 100
97.
1
over 3 over 100,
into
take the log,
half.
take the half, that will be the alpha for that classifier. Okay, so okay, so let's pretend, so that everybody sees how this algorithm will work. Let's pretend we are given 10 classifiers, K1, K2, K10, right? We are given 100 training data, for which we already know what's the expected output. Okay, so then, okay, let's pretend K1 predicted, let's say 30 correctly. K2 predicted 50 correctly. Let me make it 60. Okay, and everybody else is less than 60. Some is 35, some is 45, some is 55, and so on. Okay, as we discussed, if we have 100, then the weight of each one of these will be 1 over 100. 1 over 100. 1 over 100. Okay, so if you were creating the adaptive boosting algorithm, my question to you is, which one first you will pick? Out of this K1.
The higher than 50, so 60.
So if K2 has the best prediction, 60 out of 100 it predicted correctly, right?
Start with that one.
So you'll start with that one, exactly. So K2 will be our first classifier. Okay, but now the question is, what will be the weight of this classifier? Okay, so the weight of the first classifier will be created through this equation. What will be EM in this example?
We have 10, right? So it will be 60 over 10. No, 10.
1
10
minus.
The definition of, once again, WE was, right? The samples that have been incorrectly classified. So in this case, how many will there be for K2?
40.
40.
Yep.
So 40 over 100 will be the sum of all of, because each has a weight of 1 over 100 in the beginning.
And then over 1, right?
Then over 1, which stays the same. Okay, so,
1 minus
so this
40
will
over
be
100.
1 minus 0.4 over 0.4
60 over 100.
log half will be the weight of that classifier.
Yep.
Everybody agrees?
Yes.
Okay,
Yeah.
so the first step is extremely easy, right?
Yeah.
Okay, now let's go to the second step. So K2 has been picked. Now what are our remaining pool? K1,
One, two,
K3,
yeah.
and K2.
99 more. Or
No,
9
10.
more, 9 more, 9 more.
10, we have just 10.
Classifiers are 10,
9, so 9.
so 9 are remaining, right? Samples are still
100.
100, right? In the beginning, what was the weight of each one of these?
1
1 over 100.
1 over 100. So the intuitive idea is like this. Think of it this way to understand what is adaptive boosting doing. Okay, in the beginning, everybody is important. Like all of our test data is important. So we picked the classifier which did the best on this test data, right? Now, second time, what we want to do is, let's say K2, how many of these were correctly classified or incorrectly classified by K2?
60, right? 40.
In our example, we know 40 were incorrectly classified, correct? So forget all the math, just let's look at it, complete intuition.
So now,
Those 40, should they be, that were incorrectly classified by K2, should they be considered more important than the next iteration or less important?
more important, because we want to
More
see
important,
if there's
because we want to see which one of these now does better on those 40.
40, correct.
Oh, yeah.
But we can't ignore all of them. So what we do is we relatively increase the weight of these 40 more than the rest. Okay, how do we increase the weight of those? So that is done
You just should, I don't know.
by this. So update the weights for the next iteration. Okay, so this equation basically, if you recall, the error was defined e raised power some yi alpha m k something km of x of I, something like this, right? Okay, so if I did basically e to this one, okay, you will see if you did the exponent of this, what will happen? Okay, this will become, or let me even give you another way to think about it. Okay, we had 40, not the first 40, but anywhere in our data set, which were incorrectly classified by K2, correct? So do we want to increase their weight? Yes. So we increase their weight by e to the alpha n. Okay, and if you take a look at exponent of this will become e to the half log of 1 minus em over em, right? Okay, which is same, if you recall, a log b is same as log a to the b.
Oh, so that's why it is squared.
So the half can go over here,
Yeah.
and this can go there.
Yeah.
Now what happens to e and log?
Cancel.
Cancel.
It's not.
Anyway, and this is the existing weight of that. So existing weight multiplied by this e to the alpha m will further enhance, increase that weight.
Yep. Oh, it was just plugged in. I'll let you know.
Yeah.
No,
Yeah.
not yet. Nope.
Maybe-
On the bottom right, you can see if it's not.
You can plug it in here, Professor, maybe on the spike.
Oh,
Okay, so I'm going to take it easier, but if this goes off, then this whole, we lose the lecture.
okay, so anyway, back to over here. Those that were incorrectly classified by K2, their weight will be increased by this factor. So this is the existing weight multiplied by e to the alpha m. And those which were correctly classified, we should reduce this, their contribution in the selecting the less. So correspondingly, the correctly classified, whatever the current weight is, we multiply e to the negative alpha m, which is basically, if we do this, becomes the square root of this, right? So this is the algorithm. So let me now show you a better explanation of this, and again on the website. Okay, the last link over here has the data boost example. So it's a small PowerPoint. Okay.